So today we will discuss the circular motion. Right? What is a circular motion? Any motion in a circular path is a circular motion. Right? So circular motion. So now I have drawn up. It is a path of an object which is here at a point A and is moving along this path. So can you tell me during this motion if this particle is doing a circular motion? See, let me mark some point. This is B, this is C, this is D. So if you see, when the point is moving from A to B, this part AB is a part of a circle. Right? This point O is the center of the circle, and this length OA is nothing but the radius of that circle. Right? So this part AB is the part of a circle. So from A to B, the particle is doing a circular motion. Then again, when it is moving from B to C, it is also doing a circular motion, but then BC is the part of the another circle. Right? So particle is doing a circular motion when it is moving from A to B, also from B to C, then again from C to D. Let me draw a new path. A person is moving in a straight line. Okay, so it is what? It is a straight line motion. Can I call it as a circular? He is doing a circular motion. See, the straight line is nothing but the circular path with a radius value of infinity, right? So this straight line will have a radius value of infinity. So we can also say that the straight line motion is also circular motion, but having a radius value of infinity, right? So as we discussed earlier, like terms like displacement, velocity, acceleration, in this chapter also we will discuss those terms: acceleration, velocity and displacement. Along with that, we will also discuss some new terms like angular displacement, angular velocity and angular acceleration, and also the centrifugal acceleration, tangential acceleration. All these terms we will discuss. So let me start with the term angular displacement. So what is the angular displacement? Now suppose an object is doing a circular motion. It is the center of the circle and he is here and it is a starting point. It is moving in this direction and object has moved from A to B. So in moving A to B, let me join these 2 points first, O A and O B. You can see here the line OB is making some angle, right? So this particle is moved from A to B, then he has displaced with making some angle, means he has the angular displacement of angle theta. This is nothing but the angular displacement, right? This new term is nothing but the angular displacement theta. Right? And if, as we have discussed earlier, the simple distance is nothing but from A to B is the length of this arc, that is suppose L. So the simple L, right? So, and suppose the radius of the circle is R. Okay. So now, suppose we know the value of L. Can we find out the value of theta? We have already learned it in the previous classes that the angle is nothing but the R upon length or R upon radius. Right? So here the R is nothing but the L, right? And the radius is R. So simply we can find out the term theta if we know the distance L with this formula. How did I get this formula? Can you derive it? So now suppose this is angle and this is the displacement. Now suppose the point A, an object is moving from here and he has completed a one. So again it has come to the point A. Okay. So how many distance he has covered? If the radius is R, that is this length is nothing but the perimeter of the circle, that is nothing but the 2 pi r. And how much radius he has moved? See, the unit of the angular displacement is nothing but the radian. The angle, the SI unit of angle is nothing but the radian, right? So in the same way, the angular displacement will have the unit of radian. So what is the unit of angular displacement? It is radian. So how many radian the object has moved? It is a 2 pi, right? So now suppose the object has moved only a 1 radian, then how many distance he will cover when he will move 1 radian only. So 1 radian, I will divide this length with this angular displacement 2 pi, then the distance he has covered in 1 radian will come, right? So that is nothing but the R. So if the object has moved 1 radian only, then the distance he will cover is nothing but the R. Okay. So now it has moved theta radian. So simply I will just multiply this term with the theta, right? So it will come as a theta into R. So if the object has moved theta radian, then the distance he will move is in theta R. So from here, that is L theta that we have derived. So from here, you can see that the theta will be L upon R. So this was the derivation of this formula that we have learned in the previous classes also. There is nothing new, right? So SI unit of angular displacement nothing but the radian. This angular displacement is the axial vector, right? As we have discussed, displacement is the vector term, distance is a scalar term, velocity is the vector term. In the same way, the angular displacement is the axial vector, not a simple vector. It is a axial vector. Okay. So I want to find out the direction of the theta. See, if the object is moving from A to B, you can say it is moving in a counterclockwise direction, right? But it is incorrect. In actual, if I want to find out the direction of the angular displacement, okay, it is a very simple rule. Use your right hand. You move your right hand in the direction of the motion, then the direction of the thumb will give you the direction of the theta. Okay, so it is coming out of the plane right now. Okay, if the object is moving in a xy plane, it is a x and it is a y plane, then the direction of the theta will be nothing but the x outward direction. Okay, so to finding out the direction of the theta, we will use your right hand rule. That is nothing but the, we have to move our arm, okay, in the direction of the motion, and the direction of the thumb will give you the direction of the angular displacement. Okay, that is either outward, if it is moving in a opposite direction, then the direction will be in the inward direction. Okay, or you can also say that it is a x and x is a y, then x is the outward direction is nothing but the direction of z, positive z. If it is moving in a opposite direction, then it will move in a minus z direction. Okay. So, see, when I am doing this, the observer is at the center of the circle. We are seeing this object moving from A to B while standing at a point O. Now suppose there is another observer that is somewhere here, okay, O dash. So, if I join these 2 points with O dash, this angle theta dash, you can simply see here the theta dash is less than the theta. Right? So, depending on the observer, your angular displacement will be different. And for this observer, we can now apply this formula. Why? See, if AB is object is moving from A to B, okay, so it is a part of that this circle. When the object is here, your center point has not changed. Your R will also be changed. That is a R dash, right? So this R length cannot be the part of this another circle. So if the observer is now from O is here O dash, there will be a new circle that will join the point A to B. So this formula we can now apply here. Because here we will get the distance L dash. Okay, that is a totally wrong because object is moving from here to here along this path. So you can, if the theta dash is given, theta is given, and this OA and O dash is given, you can simply using the trigonometry, you can also find out the L dash. Okay, so this is your homework. That how can you find the L dash if the angle is given and the radius is given. Okay, the hint is you can find out. See, if the angle is given and this radius is given, you can find out the chord line. Right? Simple using a trigonometry term. That chord line will be similar to same for the both. For this circle also, for this circle also, the chord line AB will be the same. So from this, okay, you can find out the from this theta dash and R dash you can find out the L dash. Using that L dash you can find out the tan theta, and using that theta you can find out the tan L. Okay, so it is a simple mathematics. I am not doing here. So now comes to the another topic that is the angular velocity. So what is the angular velocity? Like we have discussed the velocity term, that is a displacement upon time. The same way here, the angular velocity is nothing but the angular displacement upon time. So Okay, this is the theta. So angular velocity, we denote by the term omega. So omega is nothing but change in the or you can say angular displacement upon time. Okay. So suppose it is the base point, baseline. From here, this is making an angle of theta 1, and here it is now has moved to point B, that is making an angle of theta 2 from the horizontal. So that angular velocity will come theta 2 minus theta 1, and suppose the time was t1 when the point is here, and the time was t2 when the point is on a location B. So here it will come as a t2 minus t1. So this angular velocity is nothing but the average angular velocity. Like we have discussed earlier also, the velocity is change in a position upon with respect to time. The same way here, the angular velocity is nothing but the change in the angular position of the object with respect to time. Here we are using the term delta theta upon delta t. This delta value, delta t, when we use it, when there is a when we are calculating the average velocity, right? Similarly here, this term is nothing but the average angular velocity. Now suppose we want to calculate the instantaneous value of the omega. So what can we do? We can take the limit where the delta t is tends to 0. Okay. So when we put the limit, we can rewrite this like this, d theta by dt. Okay. So omega it is what? Instantaneous value. Instantaneous angular velocity. Okay. So instantaneous angular velocity is nothing but d theta by dt. So what will be the unit of the angular velocity? It will be radian per second. Unit will be radian per second. The direction of omega, the same way we have discussed when we are discussing the angular displacement. You have to move your right hand in the direction of the motion. The direction of the omega will be the direction of the thumb. You can also see here omega is d theta upon dt. So here the change, okay, this direction of the theta will be nothing but the direction of the angular velocity. Okay. So theta, what was the formula of theta? That is the r upon radius. Okay, that r we have discussed. That was L. Suppose the object is moving with a uniform velocity, that is a v. So this length L will be what? Velocity into the time. If it is taken the time t while moving from A to B, so the distance L will be nothing but the velocity, speed into the time, not the velocity. It is a speed into the time. Okay. So L will be nothing but the speed upon into the time. Okay, speed into the time. So if I put this value here, what will we get? See, omega d by dt, it is v into t upon the r. Okay. So if we differentiate it, okay, Okay, you will get V by R. Omega is nothing but we will get is the velocity upon the radius, and we can also rewrite this as a velocity or speed is equal to omega into R. Okay, speed is nothing but the omega into the R. See here, when the object is moving, okay, suppose this is the point. At this point, what will be the direction of the motion of the particle? Okay, at that instant, this particle is moving in that direction. The same, if we come out this position of the particle or an object is moving in that direction. So if object is moving with a uniform speed also, the magnitude of velocity will be also be the same. But here you can see the direction of velocity is always changing. So in the uniform circular motion, the speed is constant, velocity, the magnitude of the velocity is also constant. But if we talk about only velocity, then it is not a constant value. Why? Because it is always keep changing its direction, right? You can also see here one point that is when the object is moving, the direction of velocity is this, and if you join this particle with the center, you can see the direction of velocity and the radius is always being in a 90 degree angle at each and every point. The radius and the velocity is moving always to a 90 degree angle. Okay, so when we write this formula, omega is equal to V upon R, this velocity, what we will take is the perpendicular velocity, the velocity that is perpendicular to the R. Suppose, for example, when the particle is here and the direction of the velocity, suppose it is not in that direction, suppose it is in this direction. Okay, so we have to take the component of the velocity that is perpendicular to the R. Okay, so we have to find the component of the velocity, right? Okay, so this component is perpendicular to the R. So we have to take this component of the velocity. So I can also write this formula as a omega equal to perpendicular velocity. Okay, perpendicular velocity upon R. Okay, that is nothing but the component. I also write in the terms of words. Okay, so component of velocity perpendicular to R. Divide by the radius. Okay. Radius. So when we will calculate the omega, when the velocity is given, we have to check that the velocity given is perpendicular to the that radius R or not. Okay. So let me show you with this thing with the example. Okay, so example. So now suppose your object is at A, okay, it is moving in this direction toward B. Here the velocity of the object was V. Here also the velocity of object is V. Means object is moving with a uniform velocity. You have to find out the omega, that is the angular velocity, with respect to the point O. Okay. We have to find omega with respect to O. Okay. See, you can take the theta value as a 37 degree. Okay, 37 degree. So you can take the theta value as a 37 degree. Okay. If we take it as a 37 degree. When the object has moved from A to B, what will be the distance of AB? That is sin theta. Sin theta, that is AB upon OB. Sin theta, sin 37 is nothing but the 3.5. And we have to find out the AB and also the OB. Okay. So for that, what can we do? We can apply the, we can also apply the tan theta. Tan theta directly we will get the AB. Okay, so tan theta AB upon AO. Okay, AO we know that is a 4, and tan 37 degree will be nothing but 3 by 4. So AB will come out as a 3 unit. Unit is not given unit. So AB will be 3 meter. And from the Pythagoras, so OB will be nothing but the 5 meter. Okay. So when the object is at A, what was the angular velocity? That is the perpendicular component of the velocity, that is perpendicular to the R. So this is your R. And this velocity is already perpendicular to the distance OA. So here we have taken the value of the velocity as it is given. Okay, so here velocity is suppose 10 meter per second. Okay, so it is a 10 divided by the radius, that is nothing but the 4. Okay, the distance of object from the center point. That is the radius, the value of radius. Okay. So here the angular velocity will come out as 10 upon 4. That will come out as a 5 by 2 radian per second. Now suppose the object has moved from A to B. Here you can see here the observer is at a point O. The distance between O and B, we have to take this distance, that comes out to be a 5 meter. But here you can see the velocity is not perpendicular to this line O and B, OB. So what we have to do, we have to take the component of the velocity and find out the velocity that is perpendicular to this distance O and OB. Right? So we have to find the component of the velocity. So first we have to find out the angle. So it is theta, so it is 90 degree, it will become 90 minus theta. It is 90 degree, so it will become theta. Okay, so the component of the velocity that is perpendicular to OB will be V cos theta. Okay, so angular velocity when the object is at B is v cos theta divided by the distance OB. So v cos theta will be 10 into cos theta. Cos theta will be 4 by 5 divided by the distance OB, that is 5 meter. Okay, so here it's become 8 by 5 radian per second. Okay. Now see, we can also write this equation v equal to omega r as a vector quantity. Okay. So if we write this equation in the vector form, we have to write like this: v equal to omega cross r. Okay, v equal to omega cross r. You can also find the direction of the velocity if the omega and the value of the omega and r is given to you. Suppose so now your object is now supposed at point A. Okay, and object is moving from A to B. So the direction of the motion will be this. So the direction of the omega will be of this plane. Okay. So to find out the direction of the V, we have to use our palm. Okay. Now the palm we have to put our palm in the direction of the omega. So omega is the direction of omega is nothing but the outward from this plane, that is this direction, z direction. Then we have to move our palm in the direction of r. So OA is nothing but the radius of the circle. So we have to keep our palm in the direction of the omega, then we have to move our palm in the direction of the radius, then the direction of the thumb will give the direction of the velocity. So here the direction of velocity is coming out in this direction, that is the correct direction because the object is going from this direction to this direction. So obviously the direction of velocity should be in that direction. That is and that is true. So we have to put our palm in the direction of the omega, then we have to move our palm in the direction of the r, and the direction of the thumb will give the direction of the velocity. These all three terms are perpendicular to each other. You can see the omega is out of the plane, so omega is perpendicular to the r. Here r is perpendicular to the omega, velocity v, and v that is in this plane. And omega which is out of the plane, so omega and v are also making an angle of 90 degree, right? So omega and v are also perpendicular to each other. So all these terms are perpendicular to each other. If we write this equation as a suppose r cos omega, then it is a norm. Okay, you cannot write this as a r cos omega. It is showing the opposite direction. Okay, this equation is wrong. So the right way of writing this equation is v equal to omega cross r.